Hello and welcome to part 1 of this tutorial on the SVD, the singular value decomposition, and some related decompositions. My name is Michiel Hochstenbach. So first of all, we'll introduce some well-known norms. The Frobenius norm in the first place, which is defined for a vector or a matrix, and also the matrix, the operator 2 norm, which is defined as the maximum output-input ratio. The SVD is a very well-known decomposition that is useful for many applications, for many questions, such as, for instance, the best rank K matrix approximation, all kind of distance problems, like the distance to the closest singular matrix, for inverse problems, ill-post problems, and various related problems. So this SVD is a matrix decomposition that exists for any matrix, and it consists of the left and the right singular vectors that form an orthogonal basis for the input space and the output space, such that under those coordinates, the matrix can be considered diagonal. And not only diagonal, but with positive entries or 0. And often they are in decreasing order. So sigma 1 is greater or equal to sigma 2, is greater or equal, etc. The use of this, the meaning cannot be underestimated. It's really very powerful, and it occurs all over numerical linear algebra, numerical mathematics, applied mathematics. Very important. So while this is exact, this decomposition, usually what is the most useful aspect is this truncated or approximate SVD. So this TSVD is the best rank K matrix approximation. And what do we mean by that? If we look for the best approximation to a data matrix A, given that the rank of B should be exactly K, then it turns out that the TSVD, the truncated SVD, the partial SVD, gives this best rank K approximation. Not only in the Frobenius norm, but also in the 2 norm, the operator norm. The difference is that the minimum is different in both cases. And in fact, this in the 2 norm, the operator norm, the minimum is usually not unique. So that means that that the Frobenius norm to some extent is more convenient or more easy to deal with than the 2 norm. So that is one of the reasons that the Frobenius norm is often quite popular. So because of this very useful feature, this SVD can be used for many applications, as said, for instance, in this dimension reduction or feature extraction. So which are the dominant trends of the data matrix. So in fact, the singular values and the SVD occur in several other norms. So these are just 2 of the norms. So here we see some other norms. And we have seen that, like the Frobenius norm, in terms of the singular values, it can be written as such. And the operator norm is just a sigma 1. So that is one of the reasons that, like in the 2 norm, this matrix approximation problem is not unique. It just measures the sigma 1 basically. There are various other norms. So here are some examples. So the nuclear norm is relatively well known. It can be seen as a kind of Frobenius norm, but then with a different P. So this Schatten P norm, like for P equals 2, it gives Frobenius norm. And for the P equals 1, it gives the nuclear norm. So there are also other norms, such as this Kivan norm, which for L equals 1, it reduces to this 2 norm. And for L equals the rank, it reduces to this nuclear norm. So it's a little bit in between. Okay, so in the field of numerical math, numerical linear algebra, scientific computing, this is often the most frequent point of view. So we take the Frobenius norm and we just maximize over the sphere in Rn this output vector norm. And if we have captured that, we look at the space orthogonal to this first maximizing argument, and then we define sigma 2 to be the next maximum. So that is kind of the linear algebra point of view. In statistics, the SVD is also very, very much used. For instance, in this PCA, so principal component analysis, the angle is different. So the point of view in statistics, for instance, is that we are looking for a linear combination of features that gives the maximum variability. This, in fact, gives the SVD. So the PCA can be computed by the SVD, but the point of view is different. So there are various other statistical quantities that can also be expressed in terms of SVD or are related to the SVD. Usually what is of interest are the largest singular values. So there's sigma 1, which is greater or equal to sigma 2, etc. Yeah, so sigma 1 is, I said, the 2 norm, the operator norm. And often there is a quite steep decay in the sense that maybe the first singular value is already quite a lot larger than the second, maybe, and maybe the first 10 are the most dominant singular values, and the rest is of less importance. And in a situation like that, it's very attractive to carry out dimension reduction. Okay, then the question arises, well, aren't the smallest singular values of any importance at all? Yes, they are. They often pop up in various applications, such as distance problems. So if we have a matrix, how far is it from a matrix that is, for instance, singular in the square case or of a lower rank in the non-square case? Often in inverse problems, ill-post inverse problems, the data matrix may be singular or maybe not a full rank, and this is very complicated, then especially in the presence of noise. This very important linear system, just AX equals B square matrix, the sensitivity of that problem can be shown to depend on this condition number, which is the largest divided by the smallest. And that means, like, if we change the inputs, like the B and the data matrix A, how is our solution going to change? And here you see that both the largest and the smallest singular value play a role. In dimension reduction, sometimes these small singular values also play a role, but it's not so common direction. So this would give the answer, which features do we want to exclude in any case, for instance. And usually this is not so important because this rank, like the data matrix, has a rank which is much larger than the actual features that we want to preserve. So we want to cut out a lot of stuff. So for that reason, it's not so useful often in practice. This is a maybe relatively well-known slide. It gives a nice relation of the SVD with 3 different but related eigenvalue decompositions. And the operators arising here are all symmetric. So this ATA, AAT, and this augmented matrix, they're all symmetric. And this is great because symmetric matrices, we know they have a real spectrum, so real eigenvalues, and orthogonal eigenvectors in the sense that they can always be chosen to be orthogonal. And it is this nice connection that enables the SVD to be computed very efficiently, because this eigenvalue problems of involving symmetric matrices are very well known, and we know how to deal with them. Let's go to the computation or optimization. In view of the fact that we know so much about solving symmetric eigenvalue problems, we can actually make the statement that computing a T SVD, truncated SVD, or also called the partial SVD, is in fact one of the easiest possible tasks in numerical linear algebra. It is really very, very easy compared to many other difficult tasks. So what not everybody always is aware of is that this partial, this truncated SVD is usually very avoidable. So let's see how that comes about. So for small matrices, and small, you can nowadays think, for instance, dimension of about 10,000. Like this, this SVD takes order mn squared operations, where n is assumed to be smaller than m here, less or equal to. So at some point this stops. But for instance, if you try this in MATLAB, usually it is a pleasant surprise how fast the SVD routines are. They are very, very optimized nowadays. Yeah. So, but this is usually not our main interest, because this is only for small matrices up to some dimension, and it computes all of the singular values and vectors. And this is usually not our interest. So we are interested in just some of the interesting features or trends. And then we have like a distinction between large scale problems and huge scale problems. I'm just a fan of this category, large scale problems. And large is, you can think of really large. And so for instance, if the dimension is 1,000,000, if m is 1,000,000 and n is only 30, for instance, then I would say still it's small scale, because one of the dimensions is small. But if they are both pretty large, then there is a nice state of the art, and that is formed by Krylov methods. We'll come to that in a minute. And what is done is apply this A, this data matrix, and it's transposed several times to one or a few vectors. So you just usually start with a random initial guess, and then you do some iterations on that. And you can do that on one initial guess or a few, and then it's typically called a block method, like a block of vectors. Okay, there is no real nice expression like this order expression in terms of cost. The costs are usually measured in terms of matrix factor products, and we can only say that it's usually modest, and there are definitely some nice bounds, but they are quite involved, quite complicated, and usually for practical problems, this is not it's more of a theoretical nature than anything else, I would say. One of the heuristic reasons say, and I'm not going to go into this, but that it's for the efficiency, it's useful if this gap is as large as possible, and this gap is between like the first and the second, and the first and the last singular value. But then since ATA or AAT is involved, it's actually, you look at the squares, and usually the sigma 1 is large and the sigma r is small, and then there is such an approximation. So that means that this gap is actually kind of larger than the gap that you would look at for just based on the singular values alone. Okay, next slide we'll have some more details. Just some words about huge scale problems. So huge scale problems, there you can think of really situations where this data matrix is so large that, for instance, storing it on a hard disk or in RAM is already a problem. And what people then do is, for instance, apply A just once on a lot of random vectors. So instead of one vector, you take a lot of random vectors, but you apply A only once. Or for some problems, you can try to apply just part of A, so not only A the whole matrix, but just a part. Usually for the SVD, you have to apply everything of A. Okay, what is the state of the art? It is basically length by diagonalization. It's a kind of Krylov method. So in Krylov method, we start with this initial random vector, and then we just apply by A and A transpose all of the time. And the dimension of this search space is increasing, this Krylov space. So because this is a symmetric matrix, we have short recurrences. So it is efficient, but unfortunately, that was the progress of several decades. It was found out that usually we have to use some kind of Gram-Schmidt process to ensure that these vectors remain orthogonal. And at some point, this reorthogonalization cost takes over. It becomes a dominant cost. So it is too expensive. And so not so much the matrix vector products are so much the problem, but these costs to keep the basis orthogonal. And therefore you need restarts, and restarts you can think of, okay, we just take the best V so far and restart with that V. But in fact, you can do much smarter than this, and this is implicit. So you kind of implicitly compute a new V. It's very efficient. It has been known for about 2 decades or a bit longer. Here, for instance, this paper is kind of the state of the art. It's a nice implementation. As said, sometimes you use block methods. So this V is in fact not so much a vector, but a block of vectors. So for instance, if you want a rank 10 approximation, why not take 10 vectors in the beginning and go with that? And so most of the codes have this option of computing the largest singular values, but also sometimes the smallest, and they can be 0. So sometimes there's this option of smallest but non-zero. And that's, in fact, it's computationally much harder problem. So the largest singular values are at the exterior of the spectrum of these 3 matrices, and this is often much easier than in the interior of the spectrum, and that's where these guys are. Okay, this may be useful for some of you. What about the code? So having said all of this, can we try this? Can we use some software? And here is definitely, like I would say, a table to start with. So if you use Python, there's this implicitly restarted length by diagonalization method. I would say MATLAB is a kind of the basis, like is usually the first to implement something like this. But then it is often like people try to implement this for R, for Julia, for Python as well. So this is definitely the first thing to try if you want to give it a try, how fast it can be. And there are also more extensive packages. Extensive usually means there are all kinds of eigenvalue problems, like this singular value decomposition, but also just ordinary eigenvalue decomposition, generalized eigenvalue decomposition, where you have quadratic eigenvalue problems, polynomial, like cubic eigenvalue problems. There are matrix functions sometimes, also important for networks nowadays. So these packages you can have a look at if you need more than this, and often they have nice interfaces to, for instance, Python or R. And for instance, this Prim or this SLAPC, it is developed by some of our colleagues, but at the same time, I would say it's industrial quality software, so like developed at academia, but it is definitely a very, very fast and optimized package, and yeah, very popular for applications. So I'm going to make a bridge to the main parts of this tutorial taught by my colleague Sibyl. So we have here this now this data matrix, and Sibyl will talk a lot about kind of these approximations. And we have seen that the TSVD truncated SVD, and like this truncated PCA, coming from statistics, has these orthogonal columns. and a diagonal positive definite C, middle matrix. Then you have a CUR decomposition. CUR stands for, the C stands for column, and the R stands for row, and this U is a relatively arbitrary name. Here the Y and the X need to be to consist of columns and rows of D, and that is very useful for interpretation, that you can say, okay, but I know which data points or which features or it corresponds to. So this C here is full. Non-negative matrix factorization, also a part of this tutorial. Like actually you don't need this C, you can just do with Y and X. And here you need positive elements, which is really a different cup of tea compared to the orthogonal columns. So orthogonal columns cannot be all positive, that's impossible. And then the like the most severe constraint is binary, where you can say, okay, these elements are just 0 or 1, or they are 0 and 1, but we only have one per row or column. Very attractive topic, and we hope you enjoy the rest of this tutorial as well. So here, just to wrap up, here's an like in a small example where we have this data matrix, just 4 times 4 positive elements. And you see, if you do the rank 1 SVD, that is in fact positive because all the elements are positive. You can prove that. And in this case, it is also a rank 1 non-negative matrix factorization because everything is non-negative. If we go to the rank 2 SVD, you know for sure that this rank is going, this error is going to decrease. And you see here exactly the first column, and here this first element, it's exactly the same as here. This rank 1 SVD, we just have a little bit more. So you can see clearly from the SVD that this feature, first feature, is about 3 times more important than the second feature. So really convenient, this SVD. However, this rank 2 NMF, non-negative matrix factorization, it's a much harder problem. So I did an approximation here, but in practice, you often don't really know whether this is optimal because it's a very hard problem. And you see that the error is much larger. On the other hand, we have all positive elements which may add to the interpretability. This CUR decomposition, then you say, okay, I want this to be a column of the data matrix, and I want these guys to be rows of the data matrix. And then the middle matrix, I optimize so that like this error is minimal. And then you get a approximation that has the advantage that it's interpretable to go in terms of the columns and the rows. But you see here effects, this should be a 9, but it isn't. And here you even have some negative components. Yeah. Okay, just to finalize, here are some of the references. I made this really brief. Here you see the development. In the 90s, there was this development of this implicit Krylov methods. Just 20 years ago, there was this very nice paper by Stewart on Krylov-Schur, which uses the Schur decomposition to do the same. It's much easier than this theory about ARPAC. It is a little bit more limited, but nowadays this difference has been bridged. This is the this nice implementation on which this SVDS in MATLAB is based, but also this RLB in Python, for instance. Yeah, the randomized method. There's a nice review paper of 10 years ago in SciM Review. So this paper is cited a lot, but it's just a review paper, and there's much more. But this is in the category of huge scale, and so you carry out a matrix vector product only once on quite some vectors. And so this CUR decomposition, there's a nice paper of 5 years ago using DIME, which is also often used by our colleagues in model reduction. Okay, with this, I want to thank you for your attention, and I hope you will enjoy the main part of this tutorial. Thank you, and I'm open for any questions via email in the first place. Thank you, and goodbye.